we're assessing the rates being equal at both ways through the lack of change in concentration.
Right.
Really, really important point, concentration. So I want to make sure you're fully aware of what concentration is, right? That's just the amount of something divided by, and I should say the amount of a solute. Remember solute and solvent? Solute is the thing in the smaller amount, solvent's the thing in the larger amount. It's the amount of the solute divided by the amount of
The total?
the solution, whatever that is, the solute plus the solvent.
Right.
So when I'm dealing with mass, I add those together. When I'm dealing with volume, it's already wrapped together on its own, because you don't look at the difference between the mass of the solute and the mass of the solute if you have a volume. It's all together in the volume. Okay. That's an important point that I'm making clear here, is that it's the same thing you looked at in the context of kinetics. You were looking at concentrations. That's the amount of something, the solute, divided by the amount of the solution. That's how we were assessing it. And for kinetics specifically, looking at the rate law, we were looking at the loss of that, right? Because we were looking at the reactants. In equilibriums, we're looking at the gain of the products divided by the loss of the reactants at a particular point, which also means at a certain temperature.
Yes.
Right? That's got to be really clear. If I change the temperature, is the equilibrium going to change?
Yes.
And therefore, are the concentrations going to change? Yes. Right? Because if I'm changing the equilibrium, the concentrations will change, and therefore the equilibrium constant will change.
Right.
Okay, all that may sound really easy, but as I go through now, I think part of this chapter, you're going to start to see where and why I'm saying what I just said. I want to make sure it's really, really clear what I'm getting at when I get to those points. And the first one is gas phase equilibrium. So what this is basically is I could take, instead of concentrations, if I have everything in the gas phase, I could use the partial pressures of those in the same way I use concentrations to figure out the equilibrium constant. Okay, does that make sense? Everybody see why, based off of what I just described to you prior? Let me walk you through quickly, and then I'll revisit all the things I just said to put it in context why I could do gas phase equilibrium, which means partial pressures of each thing, just like I can do concentrations. It's also key to why I cannot do other things, and I'll put this in context. So this is basically just what I said. One thing I want to point out is the concentration of a gas is proportional to its partial pressure. Really the amount, right, in terms of moles, as you guys know it, from Chem 101, should be proportional to the partial pressures. What was, when we did gases in 101, what did we talk about in terms of partial pressures? There should have been at least two things that should have stuck out to you. One was Dalton's law. What is it?
The ratio of...
That's the other one. Let's start with Dalton's law. That was the easy one, if you recall, and I said it in class for those of you that had me. This is a very easy law. I just take all of the partial pressures, I add them together, and I get the total pressure. Yeah, see, when I start to say it, it starts to make sense, right? That's Dalton's pressure. What about the other? What was the other one where you could find partial pressures? We did something like a diver went a certain distance down in the water, and at a particular point of pressure, mole fraction. The partial pressure over the total pressure equals the mole fraction.
Right.
The mole fraction is just the amount of moles of that particular thing divided by the total moles.
Right.
That's the mole fraction. And then if I say the partial pressure of something equals the mole fraction times the total pressure, I can now figure out my partial pressure. Remember that? That relationship, that's important here. So that's all they're saying here is the concentration of a gas is proportional to partial pressure. And I'm really saying you guys know it as moles, but that makes sense because in a container where I'm doing a reaction, let me go back and make sure we're clear. Concentration, amount of the solute in the solution, or the, so how do we see that? In molarity, let's say, that's a pretty common concentration we've talked about. That's moles of solute per what? Liters of solution. Volume, right? I'm pointing these things out really intentionally. I want to make that clear, right? So when I talk about the concentration of a gas and I have things in a container, is the volume changing? No. Is the pressure changing as the number of moles change?
Yeah.
Yes, and there's your molar ratio compared to the partial pressure. Right? So the partial pressure of one thing. So that's why in gases, I could simply say that I could use the partial pressure as a replacement for the concentration. It also should make you think a little bit about how I'm using concentrations and why. When up to this point in the brief introduction of equilibrium that Nathan discussed, he talked about concentrations, that's Kc. What does that imply that I'm working with?
Just concentration. Or solution.
Solutions. That means I'm looking at solutions in the balanced chemical equation because I'm taking it from the balanced chemical equation, right? Do I always have solutions in balanced chemical equations?
No, they're mainly gases.
I have gases, right? Things interact as gases. What if I had something like a solid or a
Solid,
liquid? Does the concentration of those change? I take a little bit of let's say the moles of it. Does the volume change proportionally?
If you take the moles, what did you say?
If I take a little bit of an amount, let's say in moles
Oh,
of
yeah,
a
we
solid,
changed, right?
do I also lose some of the volume?
Yes.
So did the concentration change?
Yes.
Yes.
The concentration, not the number of moles.
It's still the same concentration.
The same concentration are pretty close, right? Not a whole lot changes in a solid
Okay, right.
or a liquid or a solvent.
Yeah.
So then when I'm looking at the equilibrium constants, I'm more specifically looking at concentrations and or partial pressures of gases. So I'm either dealing with things that are in aqueous or I'm dealing with things that are gases. Because if I'm not getting any change in the concentration of the solid or liquid, then what can I call that?
Is your order?
I can call it a constant. And I can wrap it all up into the Kc because it's not changing just like everything else.
Right.
Right? So I'm only worried about things that change. So keep that in mind in the context of what we're looking at and why when we're discussing an equilibrium and specifically the equation and how we're assessing what the Kc is as a relationship to that equation. Okay? So here, okay, so they want to introduce this a slightly different way, PV equals nRT. What's the limitation on PV equals nRT, just to remind me? It's what?
You need to have two of pressure, volume, temperature.
Okay. What is this called?
The universal gas.
Universal gas.
Or the
Oh,
ideal
ideal gas.
Ideal gas law. Thank you, Taylor. It's called the ideal gas. Why? What's ideal about it? They're all acting under the concept of KMT, kinetic molecular theory, right? So what's the difference between that and a real gas?
You're not factoring in the like other things like intermolecular interactions.
There are potentially intermolecular interactions that the KMT says there are not, right? So a real gas actually makes interactions, which then changes potentially the pressure and what else? And volume. And those were changes put in by who? Is that van der Waals? That name sound familiar? The same one who did the interactions? And we saw those additions, right? So this happens in an ideal gas, but not necessarily in a real gas is the point here that I want to make, right? I want to remind you of those distinctions and the differences, because we did talk about those things. So if I rearrange this equation here, and I put N over V, I basically have my moles over my liters, and what is that? Essentially, concentration, right? So that's essentially concentration, and that's equal to the pressure times RT divided by RT. R is just the universal gas constant, right? In this case, I think they use 8.31 or 0.0821. So it depends on, so usually this is going to be in ATM, liters, Kelvin, and then the R would be 0.0821. So the molar concentration of gas is this. This is just, all I'm doing is rearranging stuff here, right? I'm just pulling the RT over from the P. And this is all a constant at room temp, at some temperature. And so my only variable points are these. But if you recall in a reaction, the volume's not really changing, right? You have the same container. So keep that in mind, even though but now if the pressure changes, right? then that means that the moles have changed. And we would see that through the balanced chemical equation from the molar ratio, right? The moles on one side of a gas and the moles on the other side of the equation in that gas. Okay, and now I can start using that as a change in a concentration or something that's related to that equation. Okay, so Kp is what we'll call it instead of Kc. It's essentially the same thing except for I'm now dealing with partial pressures. These are partial pressures, right? I'm looking at the pressure of each gas within the mixture. It's slightly different, it's exactly the same in the setup, but it's slightly different in terms of Kc. And here's a quick transition from Kp to Kc, or inversely. Kp equals Kc times the RT, which is constant, of course, at some temperature, delta N. What is the delta N part? And this is the part that makes it different, of course.
The change in concentration.
The change in moles. The change in moles from one side of the equation to the other. So if I have an increase or decrease in moles, total moles from one side to the other, then I have a difference in Kp and Kc. If the moles are the same on both sides, then what's my delta N? And what's this? And therefore they're equal. So it's only different because if I have a difference in the number of moles that I start with on the reactants and I end up with the products in terms of gases, right? The moles of gases is what I'm looking at here. So then delta means that it's the final minus the initial, so then I'm taking the products minus the reactants. Okay? And that's a quick and easy change. If I were to ask something like, what is Kc? And you find Kp, you can manipulate this to solve for Kc. Or if I give you Kc and the equation, then you can now solve for Kp without putting in all the numbers. Okay? And here's the R that we're using is from before, 0.0821, and that's because it's in liters times ATM per mole times Kelvin, which also means that you need to make sure that your temperature is given in Kelvin if you have to plug that in. And your moles are already given, so that's okay. And then moles per liter. Okay, their delta N, pretty straightforward, just the sum of the coefficients of all gas products. Coefficients because those are representing the moles, minus the reactants. That's it. Okay. So if there's 0, Kp equals Kc, you don't have to do a whole lot of, if you have one, you already know the other.
Right.
And of course, if you want to flip, this is just rearranging this in Kc. So if you're solving for Kp, you use this equation. It's easier because you plug in and you solve. If you're solving for Kc, then you just rearrange it, and this is the same thing, basically. Just rearrange. If you're comfortable just using one to solve for both, whatever. Generally, whatever you're solving for is sitting on the equal sign by itself. That's all. Just makes it a little easier to visualize. Otherwise, it's the same thing. Okay, good. So let's write a Kp expression for this reaction. So all I'm asking is the Kp expression. Once again, you're creating the Kp the same way you're creating the Kc, except for you're using partial pressures as opposed to concentrations. Okay. So what is it here? What's Kp equal here?
3.92. Oh.
Oh, does it have more question to it?
Yeah, well,
No.
yeah.
Just Kp. I'm not asking for a number. I'm just saying, what is Kp?
It's gonna equal
The partial pressure of methane
Yeah.
times the partial pressure of water divided by the partial pressure of carbon monoxide times the partial pressure of hydrogen to the third power. Right? I use the coefficient the same way as I would use it in concentration. That's all I'm asking for. You can't figure out a number from this. But just using partial pressures instead of concentrations. Is that okay? Anybody confused by this? Go ahead.
Question, so, change of N, oh, have you not got there yet, are you just doing KP?
This is just Kp, so I think if you want to make the transition to Kc, so if you want to compare Kp to Kc, then you're dealing with the delta N, right? So that would be here. I want to see the Kc, I know the Kp.
Is that switched around? Kp would be pressure and Kc would be concentration?
That's correct.
Oh, right, you switched it around. Okay, so you see different.
That's correct.
Okay.
So all I did here is just show you how to get Kp.
And just to clarify, the 3 is the superscript for the partial pressure of hydrogen.
That's the coefficient for the hydrogen, yes. So the coefficients, just like in concentrations, they are the power, or the exponent in the equation for the equilibrium constant, or in this case, the equilibrium partial pressure. Kp. Okay. Now, the Kc for this reaction is 3.92 at 1200 K. Calculate the Kp.
Oh,
So now, I already know the Kc. This is interesting, right? This is the very first time I'm giving you where you actually have the Kc. I'm not asking you to figure out concentrations, because it's not, even though I give you Kc, I'm asking you to figure out Kp, even though I'm not asking you to figure out the partial pressures. I'm pointing all of these things out because these are all kinds of things I could ask you. But for now, I'm simply saying, here is the Kc. What is the Kp at this temperature? And from that information, you should be able to figure out the Kp. So of course, what do I use initially?
the
Kp equals Kc times RT to the delta n. Do I know R in that equation?
Yes.
Do I know Kc in that equation?
Yes.
Do I know T in that equation? Yes, and if it wasn't in Kelvin, would I change it?
Yeah.
Yes. What else am I looking for then? The delta n. And what is the delta n here? 2. 1 plus 1 is 2 minus 4. So it's a negative 2.
1 over that squared.
And that would be that's my Kp. And then you just plug and chug in your calculator. Which I get 4.04 times 10 to the minus 4. What's the unit for the equilibrium constants? So far you've seen 2 of them, Kc and Kp. None, thank you. There aren't any units. Okay, go ahead.
What was the point of putting the Kp of the pressures of the CH4 and H2O over the rest? Like, was that just to conceptually understand it, or was that part of the?
You mean in the first,
Right before.
in the previous slide? Just to make sure it's clear what's happening. If I had some of those, maybe I could then solve for Kp as well.
Yeah.
It depends on the information I'm given, will depend on how you use it. So absolutely, I could have just said, well, I'm asking here for Kp, giving you Kc, but what if I gave you a couple of the partial pressures and then asked for Kp? You could have used it. There, in other words, there are multiple ways to get the Kp, and I'm demonstrating all the different things that it's related to and then how to solve for them. Okay, let's do example 2. This is fun, right? Not too hard? That's always fun. Understandable, that makes it even more fun. Kp for the formation of NO, at 25 degrees. So for the formation, that's interesting, okay. So is 2.2 times 10 to the 12th. What is the value of Kc at this temperature? Let me see your notes.
Oh, the
You have this
Yeah.
on your.
was into now. Oh, you just give us
I want to point out something here. Doesn't make sense to me. It says for the formation, so really it's going to NO2 there, not NO.
Oh, for 10.
There's a reason why I point that out, because if I was asking the other way, I would actually have to flip it. And then the reactants and products would be different. And that's gonna become an important point as soon as I teach you the ice charts, is what direction you're actually looking at. So let's say that we're looking at the KP for the formation of NO because of NO2, because this is the formation going this way, which makes this the product and these the reactants, which then changes the delta N, of course.
What would be the other way? So KF would be NO2 would be the product?
Flip
What
it.
would the other,
Flip it.
or like what would you say in the word
The
problem?
product would be the NO.
You just flip it.
and
Remember we did the manipulating case?
Yeah.
Yeah.
It'd be exactly like that, except for now you're dealing with partial pressures instead of
How would you
concentration.
How would you
label
call
to
it?
know
Like
when
this
it
one's
makes sense?
K of formation, what would you call it though?
K of result.
Oh, I see
Yeah,
what you're saying.
yeah. What would you
K,
call it?
you could say KP of, if you're going this way, it's formation. If you're going the other way, there are a couple different terms: degradation, breakdown.
But it's basically.
Anything that says you're dissociating this
Okay.
Dissociate.
is what you would look at. So you would say but you would say the dissociation of NO2 or the formation of NO. Either of those would cause you to flip this.
But not decomposition, right?
Decomposition of NO2.
Okay.
Right, you can also say, you can say any way that means exactly what it is you're doing.
Right, bring it in now.
So in this case, so anyways, getting back to this, I don't think that was the point of this, I just noticed that as an error on it. Which is important later on, because I don't want you guys to read something and then go back and look at this and then not understand why I said something different later. So I have KP, blah, 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 is this, so I'm looking for KC. So I say KC is equal to KP times 1 over RT to the delta N, to the power, right? And my delta N is what here? 2 minus 3 is minus 1. What's my R? 0.0821. And what's my T? 298. Right, 298, okay. So we're all on the same page. So there's the delta N, that's the one you have to figure out. And then I put it in here. And I simply plug in my calculator a few things, and that's my KC. What's that? Oh. What if, clearly it wouldn't be balanced, but let's assume it was balanced. What if this was only NO plus O2 gives me 2NO2? Then what would KC be?
If this was,
I'm assuming it's balanced. Let's assume it's balanced. And I have NO plus O2 gives me 2NO2. What is now the KC?
oh, let me do it.
2.2 times 10 to the 12th, that's KP, because now you would have 0
Right.
for the power there. Okay, just make sure that's clear. Go ahead, Aura.
So where the fraction is, so it's under 1. Why is there still a, to the power of -1? Is that wrong?
That's the change of N.
2 minus 3
Oh,
is minus 1.
Yeah,
But
that's the delta N.
without
But it
that,
should
wouldn't it just be 0.082 times
If you
298?
solve for
Why is it
KP, you have to.
You get
You
zero.
have to divide on this side, but then you have to flip it again.
They're using the KC, not the.
Oh,
So you have to
this,
solve
I see what you're asking. I wasn't clear on what you were asking.
He's using,
Um,
we're using this one versus he's using the one that's solving for KC.
Oh, I think it's.
Is setting it up like
So
this
then,
Yes.
wrong?
when you
Rosh.
switch the sides, that's how ours.
KP or KC? I just rearranged it. First one I solved for KP, this one after rearranging it, I'm solving for KC.
Yeah.
You could just use this and rearrange it and you would see this come out that way.
I have a question.
Mhm.
Is arranging it like this considered wrong? Then having it
Well, yeah, if it's the negative, it's fine.
Without.
You already applied the negative, it's fine.
That's the same thing.
But then
same
that-
thing, right?
Okay, let's see where we at now. Okay, so we did a couple of those problems. Okay,
I don't have a calculator.
so we're okay here? Everybody okay? This makes sense?
Yep.
No big deal? Okay. Okay,
You can use that.
so now,
That's too complicated.
okay, so this brings up exactly what I already brought up to you to start this lecture, right? Is we looked at concentrations for the KC, we looked at partial pressures for the KP, but if I had an equation that had other things in it, like solids and liquids or solvents, then those concentrations, assuming they're not gases, are not going to change much. They're basically constants. There are situations where they could change a little bit depending on the situation. It's a little odd because you're actually supposed to look at the activity of them as opposed to just the pure concentrations, but usually the activity and the concentration or the partial pressure are almost the same thing. They're basically the same thing. So they kind of assign it as one and just move it over as its activity and then just move it over to the constant because it's not going to change much from one side to another. So I'll elaborate on that a little bit, but the main thing that I'm getting at is you're looking at the physical states of the reactants and products. When you don't see a concentration or something that's capable of a concentration change, like aqueous, or you don't see gas from partial pressure or also changes, then you simply think of it as a constant and move it over into the constant, Kp or Kc. Okay? So let's take a look. So I guess first we're going to talk a little bit about homogeneous equilibrium. What does that mean? Because you just learned homogeneous catalyst and heterogeneous catalyst. What did homogeneous catalyst mean? Everything's in the same phase, the same state. That's the same thing with homogeneous equilibrium. At equilibrium, everything's in the same phase. And then, of course, heterogeneous, they're different. And that's the one that we're getting to right now. Okay. So this should be simple just because if you think of it the same way as a catalyst. Equilibrium that involves reactants and products in a single phase, in other words, are all gases or whatever else. Okay. And here's an example, gas, 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 gas. In other words, what am I doing is I'm prompting you that you now have to pay attention to this as we learn and increase our knowledge in equilibriums. You now have to focus and pay attention to these things which initially we didn't talk about. Right? Okay. Make sure you now, every time you look at something, you got to be aware of this. Okay. So that's how homogeneous, heterogeneous, as you know, is where you have different phases, and here you have a solid, a gas, a solid, and a gas, and that's kind of the point. The term here, homogeneous, heterogeneous equilibrium, not that big of a deal. How you utilize that information is a big deal. Okay? Make sure we're clear on that. Okay, so there's the difference between solids and gases. Now, that sets us up for this here. Constant expression can be written with pure solids included, as well as pure liquids, as well as solvents. Solvents are basically the same thing as a pure solution, or just something that's in abundance, obviously. So therefore, the change wouldn't matter that much. So this is everything I was talking about when we started today. If I take a solid, and I say it has some mass of whatever per volume of it, right? And then I take a little bit away, the concentration did change. Took a little mass away, but I also took a little volume away.
Right.
So the concentration is the same.
Yes.
Didn't change. That's the point. And that's the one that most people get really stuck on. The same thing is if I had here, let's say I have something in here, just one thing, and that one thing is aqueous. So I'd say I have, let's say, 5 molar of something in here. I also have a lot of water in here, right?
Mm-hmm.
If I take a little bit of the water out or in, is that going to change, if you think of water as a concentration of the water? One way you could think about that also is the density. Would the density of the water change? No.
No.
Density is the same thing, right? Mass over volume.
Right.
So those things are not changing. As a result, if I change the temperature and I increase this going one way or another way, as a result of that change, the solid parts are not going to change in the context of what Kc is representing, which in this case are concentrations. So therefore they're constant. They don't change. Yes, you need to use some to get here, you need to use some to get here. But the concentration, which is what you're representing the Kc of, does not change. That's the point. Okay, and as a result of that, they're basically constant. So the solids are constant. I could wrap all these up into the Kc. It's now part of the constant. In other words, I don't use the concentrations of solids, liquids, or solvents in the Kc equation. I use it in the Kc itself because it's not changing. Whether I increase or decrease the temperature, I'm not going to get enough movement. Now, once again, there are exceptions in rare cases where you can find a change there, but we're not going to run across that in this class for sure. Okay, so you're not going to worry about it. Go ahead.
So like for dry ice storage, they keep it pressurized, like whenever they store it.
Okay.
Does that kind of play a role? So like, you're not as much as subliming as quickly?
So let's keep this in context of an equilibrium reaction, right? You're talking about just going from a phase change. There's no chemical reaction occurring. You're just talking about one thing in a phase change. Here I'm talking about a chemical reaction that settles at some temperature as an equilibrium. If I don't have the equilibrium there, none of this matters anyways, right?
But pressure will affect the equilibrium.
Pressure will affect the equilibrium of the chemical reaction.
Oh, okay.
You're now asking about a physical change going up and down, not a chemical reaction.
I see.
That's where I'm trying to distinguish it. Yes, we could talk more about that, but I don't want to sidetrack anybody into that thought process because it's different. Okay, so I want to keep this. We're talking about a chemical reaction here, not a physical change. We're talking about physical states of the things that are playing a role in that chemical reaction. But we're not talking about just one thing and its physical change status. Okay. Okay, so all I'm going to do here, I'm going to rearrange this as you can see. I'm going to move these things, which are here. I'm going to move that down. I'm going to move this one up. I'm going to wrap it all up and call it Kc prime or something. Just a different constant factor. I'd call it K whatever. I think they'll call it Kc prime is what I'm assuming. Yeah. Or, yeah, Kc prime. There's prime. We call it node, Kc whatever. It's essentially the same, it's just Kc, but I don't have the concentrations of the solids, and if I had pure liquids, of course, not things aqueous, pure liquids, those would also be all wrapped up into that. And ultimately, that's what I get. This just includes, in this example, pure solids, but it would also include pure liquids. And if you had a solvent, pure solvents or whatever else. Okay, does that make sense? So hopefully I define that clearly because that's a big sticking point of people it's not that you can't follow along with doing it, but you don't understand why it's done. And hopefully that clarifies why you could just put this as a constant because you have very little or no change as a concentration or as a pressure with a solid or a liquid. Okay, I think this is just an example of that. So here, it's supposed to show you that you have a solid here, and you have the same temperature in both. You have the same concentrations of CO2, CO at equilibrium. You're in a closed environment. And then if you come over here and you increase the amount of CS, whether you take some away or increase it, the concentration of this doesn't change from here to here. It stays the same. The amount of it's different, but the amount per volume is the same, and that's the key. Okay, and that's all this is supposed to show you. I think this is put in because it's part of the book or something, but if the explanation was clear enough up to this point, this is just to allow you to see that. Once again, it doesn't tell you that, though the main thing here on the screen is that the concentration is not changing because that's what you're using within the context of the Kc, or the Kc prime is now we're adding to. Okay, so I want to write Kc here. How do I write Kc here? Kc is the concentration of what? H2O over the concentration of H2. That's the Kc. What did I do? I just wrapped up I don't include the solids. So now I'm evaluating these here, and I'm saying, do these things here play a role? If it's a solid, it does not. If it's a liquid, it does not. At least in terms of the Kc, if I were to change a condition and how it changes the equilibrium, those do not play a role in it. They do play a role in the Kc, which is as a constant, which is why they're all wrapped up in the Kc, as I called before, Kc prime.
Would aqueous be included as something that doesn't involve that's stuck in Kc?
What do you think? You tell me. Based on all of our discussion today.
Because you said solutions were included in Kc, so I'd say yes.
Absolutely. Right? Because its concentration will change.
Okay.
Okay. So, that's it. That's my Kc. All I did now is I added on this concept of these things do not change. I could put them there, but they're constant. They're not changing. So I just can wrap them up into the Kc, which is a constant on its own. Identify each of the following equilibriums as okay, sorry there. Is this homogeneous, heterogeneous? It's kind of one of those simple questions. If you got this, you'd be very happy on a 102 test. Is
Homogeneous.
it homogeneous? It's obviously homogeneous. Like gas, 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 gas. If you missed it because you didn't come to class and you weren't going to do well on that test anyways. Right? That's pretty straightforward at this level. So there's your homogeneous. And now it says write the KC expression. Well, that's something you guys also would like to see probably because that's pretty straightforward. Okay.
And so you don't have to use KP if it's a gas? KP is just an alternative to use?
Depends what you ask for. You can. But it didn't ask for KP here. But if I did have some information on KP and wanted KC, I could manipulate that too.
But with gas,
You can write
still
KP
use
here.
KC?
Yes, if it asks for it. Right, because you can
Yeah.
still deal with, so in this case asking for KC, but it also could ask for KP. In fact, the only two things you really care about are what? Gas and aqueous. Right? So you could write it as either or ask it as either. Identify the following equilibriums as homogeneous, heterogeneous. Again, wow, just in case you didn't know. Right, okay, I don't even want to ask you guys that. Genius. KC expression, what's the KC expression? This is interesting.
Over CL to the square.
Yep.
Yeah.
1 over CO2 concentration squared, absolutely. No big deal. And now you guys are all prepped to Y. So you have an intellectual understanding of Y, and now just doing it on an exam should be pretty easy, right? Of course, I'm going to make this a little more challenging. I'm just building you up, but I want to make sure I don't lose you along the way so that you do take each step seriously, because if you bypass a step and you get to the end point where we're getting to, then you might make some mistakes,
Yeah.
right? Okay, so for which reaction does Kp equal Kc here? A, B, how many do I have? I'm afraid to click another one just in case
Oh,
it's,
no, there's no.
how many are there? 3? Okay, good. If I click another one, probably the answer pops up and then I got it. Sometimes they're 3, sometimes they're 4. I don't look at these prior, so. For which reaction does Kp equal Kc? Okay, that's kind of an interesting question, right? You kind of have to take, it's not one I've directly asked you on the slide, but I have made mention to it multiple times. When would Kp equal Kc should be the first question without looking at any of these.
When it's 0?
When what is 0?
The
Delta N.
Right.
That means that when I have an equal amount of moles of gas on one side and the other,
right.
that should be equal. Which one do I have an equal number of moles of gas? The first one, how many moles of gas on this side?
4. Oh, sorry.
2. How many moles of gas on this side?
4.
That's
2.
not going to be it.
3.
What about here? 3? 3, I don't even need to check that one. That one definitely. Now, if the question asked potentially more than 1, then I would check it. If it's 1 on an exam, I stop there, I move on. Why do I want to double check? But if I did double check, I have 2, 3, and 0.
Right.
So only 2 could be the right answer here. Oh, good, it shows you. Delta N equals 0. Is that okay?
With only when delta N equals 0, it's not.
When Kp equals Kc is when delta N equals 0. Because that
Well, the
means that
gas-
the
you don't take
RT
consideration
in
of
parentheses is equal to 1. And therefore Kp
Right.
equals
You
Kc
don't take
from the
consideration
equation
of
itself.
the-
Yes, 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 yes.
We don't care about the solids, right?
That's right, because they aren't actually changing.
Correct.
Yes, they're not changing. That's exactly right.
Also the
Right.
liquids.
So what does that mean, for example, here? I have 2 moles of gas here, and I have 1 mole of gas there. What can you tell me about that reaction? Remember, it's in a container, right?
Right.
It's not just open and we've got a container, and I have 1 mole at the end of this and 2 moles here. If I were to add, what's happening? Let's start with that. Pressure is changing, absolutely. I have a greater pressure on this side than I do this side, right?
Correct.
So then if I added more pressure to this system, not temperature, which is something I've talked about a lot in changing the conditions of the equilibrium, how would that change the equilibrium here?
It's just products.
I've added pressure to where there's more pressure in the same volume. It wants to relieve that pressure, and how would it do that? It would shift equilibrium towards where there's less pressure.
Right.
Absolutely. It's just, that's Le Chatelier's principle, which we're moving towards at the end of this chapter. Now you already know that part of the chapter, right? It's just to put this in context, okay? But you can also now see what's happening and why these things matter, right? Would the pressure would this solid influence the pressure at all? only the gas would be. Okay. Good. I like where we're going now.
Calculating.
Good. A lot of words. Usually that's not very valuable in teaching. That just means you don't really know what to say, and so I'll just use this. So I have this reaction here, all gases. I'm looking at this, I have 2 moles here and 2 moles there, so the pressure on each side is not changing. And I want to know a little bit about the equilibrium constant. So one thing I could say is I could get the Kp or the Kc by just doing my thing here, but I don't know the concentrations. Okay. Now, therefore I can't actually tell you what the Kp or the Kc is. However, if I gave you the Kc and I gave you 1 or 2 of the pressures or the partial pressures, or allowed you information to solve for the partial pressures or the concentrations, then you could solve for the ones that you don't have through the equation you already know. Okay. I have to give you those in the context of at equilibrium, right? Okay. But can I also find information out if I had the initial concentrations, let's say? Can then I figure out what the concentrations in equilibrium are, and therefore the Kc or Kp, whatever else I'm looking for? Yes. And that's sort of where we're moving towards at this point. So if I just gave you, and this is going to sound strange since it should be really, really obvious, but we just haven't done it. If I just give you the concentrations of these at equilibrium, then you can solve for the Kc. That seems a pretty simple concept, but we actually haven't done that, have we? Yeah. Right? So I could do that. What I'm also telling you is I could also give you the initial concentrations of the reactants and therefore solve for the equilibrium concentrations. There's a way to do that. That's called the ICE charts, and we'll do those. And then if I give you the Kc, I could potentially find what some of these concentrations are. So I could go either give you information to get the Kc, or I can give you the Kc with some information to get the concentrations at equilibrium and at initial. I could, depending on what I give you, you can solve for a multitude of things. And that's what we're moving towards here. Okay. So here, like I said, the very first part, very, very simple. You just haven't done it. You already know how to put together Kc here. I'm giving you the concentrations. I'm assuming these are concentrations, and you must read this. This is important in a problem. I'm letting you know that these are concentrations at equilibrium. Because if they're not at equilibrium, you can't throw them in for the Kc, right?
Yeah.
I know that seems pretty straightforward, but it's not something we've actually talked about. And if you're not familiar with it, it means you're a novice. That means that you would make that kind of mistake. If you must make sure what the concentrations that you have are, right? If they're at equilibrium, then I could solve for Kc. What if they're not at equilibrium?
Then you can't solve it.
Then I don't know what Kc, but I can solve for a K something. Whatever the K is at that moment. And if I know the Kc, then I know which way the reaction's going to move, right? Mm-hmm. So we'll call that a quotient. We'll call that Qc. Mm-hmm. And then we could see which way, remember, these are equilibrium, so you got something going this way and this way. If I know the Kc, and I give you concentrations that are not at equilibrium, then you could solve for the Qc and see where that is relative to the Kc. If it's less than the Kc, I'm moving this way. If it's more, I'm moving that way. If it's the same, it is your Kc. I just didn't tell you those were the equilibrium concentrations. That makes sense. Mm-hmm. Right? And once again, concepts seem really easy. Hopefully, I'm putting them in the proper context so you understand them, but don't get confused and think that I could just go home now and then come back to the exam. Practice it. When I'm not on your shoulder telling you what to do, it's not as easy. When you could do it without me, on your own, it becomes really easy. Okay, so don't get confused about that.
We could use any of them, right? But as long as they're from the equilibrium chart?
I'll get to that.
Okay.
We haven't got there yet,
Okay.
right? Okay, so I'm prefacing all these things of what you're looking at and why, and then what to do with them or how to figure things out, and what things to be aware of, right? So here I'm telling you, these are at equilibrium. So if they are, I can easily solve for Kc here, right?
Right.
Just plug it in, plug and chug. I can solve for my Kc. They're all gases. They come in here. I plug in my numbers, and I solve for it, and I get something, and it's 5.0. Looks like 50. 50 would be the Kc.
So once we know the Kc, and like you said, that we can actually get the K at a different, not at equilibrium, and we would actually be able to see where where it's actually
Yeah, so let's say I
going.
gave you some non-equilibrium concentrations, is what
Right.
you're asking. And they gave me a number of 5 times 10 to the minus 1.
Right.
Where am I at relative to equilibrium in this reaction? Looking at the member. By the way, let me do this before I go any further. In these, you must know the chemical equation and understand what you're looking at.
Right.
That's going to play a huge role in the next chapter and the following chapter is having your base. This is all coming off of the balanced chemical equation I'm evaluating these things from. That's where your KC is coming from. That's where these are talking, we're talking about these. And where you are in this equilibrium, this is not a straight line. This means that I have things going both directions. That's hugely important. So when I look at this, I'm now saying, if I gave you something that gave you a KC, different concentrations, your KC was less than this, that means that it's still moving towards equilibrium in this direction.
Right.
And if it had more than this, that means it's now moving in this direction until it reestablishes its equilibrium. What would do that? If I change the temperature.
Okay, so that
If
was
the
not gonna be the
pressures
same.
change. A variety of different things I could do to change the conditions that would now shift that equilibrium.
Right.
And the numbers you're getting here may not always be the equilibrium. You must evaluate. If it tells you it is, then you can simply solve for your KC. Sorry, go ahead. You had a question? Did I answer it?
No, actually, yeah, I was thinking about something. It's funny because you asked, I didn't raise my hand, but you like read my mind. I was thinking, if the equilibrium constant was like 100 and something, like let's say 120,
Okay.
it's still happening in equilibrium, but it's just more of a forward reaction.
It means that at that condition, that's where the reaction, that's where the concentrations have stopped and stabilized.
Okay.
If I now insert something into the system that changes the conditions, it will now reorganize itself to fit a new equilibrium, and that equilibrium will have its own constant. Which is why the kinetics were done first, even though they feel like they don't really fit, right? If I do something to speed up one way or the other way, it could still get to the equilibrium, but then if I infuse something that makes one way harder or the other, then it may adjust its equilibrium based on those conditions. Okay. What do I have here for reaction? More words. Okay. Let's see what they're getting at. Okay. Okay. So that was in regard to this. This is just saying that in a basic reaction. So in this case, we're looking at H2 plus I2, I'm looking at this here, H2I2 gives me 2 HIs at 445 degrees Celsius. Then it doesn't matter what my initial concentrations are, it will still find its way to the same equilibrium, and therefore the same equilibrium constant. But if I change the temperature, then it will matter. So what will matter in this case here, in the initial concentrations? I'll get the same equilibrium constant because it will equalize at the same no matter what, at that temperature. And assuming I keep activation energies and anything else that's involved the same. So if I had, from kinetics, chapter 14, if I had more initial concentration, what would that do in terms of the equilibrium constant? It will be the same equilibrium constant, but what would it change? The speed it gets there, right? So the kinetics still work. I increase concentration, generally, by the way, that's general, because we did see cases where I increased the concentration by double, and what happened to the reaction? Didn't quite double, right? Those were our, right, remember those were our half and our right. It's at different orders, whatever. But let's assume I increase, and it's just the mechanism is just one simple cross, and I increase the initial concentrations, I'll increase the speed that I get to the equilibrium.
Yeah.
But that's it. I'll still get to the same equilibrium constant as long as I'm not changing any conditions. Conditions are all the same, really, really important.
Okay.
So the initial concentration does not matter for the equilibrium constant, but it does matter to get there faster or slower. And that's all that slide was. And that's all the words on the last page we're trying to tell
You're
you.
saying changing concentration changes the rate, but not the concentration of equilibrium.
Yes, at the same conditions. Okay, so when equilibrium concentrations are not given, okay. This is exactly what I just said before. Here's our first introduction to ICE charts. ICE, I-C-E. It's a chart and you have your initial I change, C, E, equilibrium. That's your ice chart. Become familiar with it, and it will get more complicated. This is the very first part that will be easy, and it won't get that much harder if you understand it, but it does get more challenging than what you're going to see here. What you want to put, you have your ICE, you don't have to write the rest, just that should tell you enough. And then up top here, you're putting your actual equation. Hence, you need to know the direction the equation is moving. And you have your A for here, your reactant, and B, your product. So ideally, you have an arrow here to illustrate. That's why this one's not very good. It doesn't show you how you should start doing them right away. And what I've told here is that, let me do this. Generally, unless given differently, your initial concentration of your reactant is going to be something. What's your initial concentration of your product?
0.
That's 0. You already know that.
Right.
Okay, something to keep in mind. So here I'm telling you it's 1 for this concentration, and this is 0. Then at equilibrium, I'm saying that this is now 0.75.
I'm missing something.
So what was the change? What's the change here?
Oh, yeah,
0.25. Did it lose or gain 0.25? It lost. So this is a negative 0.25.
Right.
What's the ratio here? 1 to 2. So if this is a 1 and this is a 2, that means this changed 0.25 positive,
Right.
is it increase, times 2, which means it changed 0.5. And therefore 0 to 0.5 means that at equilibrium it is 0.5 concentration.
And you just disregard the negative sign.
The negative sign is here because of the change.
When you lose something, you gain from another.
So when you lost this, you gain this. So this should be minus 0.25, this should be plus 5, and this should be plus 5, or just 0.5. Okay? And that's a nice chart, and that's how you manipulate it.
So times 2 because of the molarity concentration. Okay.
What's that?
E is the difference.
Is the
E is the equilibrium. Initial change equilibrium.
But it's the difference between I and C.
Whatever you start with, whatever you lost or gained, then becomes your equilibrium concentration. And that's how the very first example I gave you the equilibrium concentration. This time, I'm giving you the initial concentrations, and you're solving for the equilibrium concentration, but you must know, of course, this. If you don't know that, you don't know it's a 2-to-1 ratio there, you don't know what necessarily to do.
Right.
That's your first introduction to ice. Get used to it. No ice. Ice is now going to play a prominent role in your life for at least the next couple months.
This is the easy part.
Yes. Okay. Now let's take a look. Oh, by the way, now that I have this,
Mm-hmm.
can I now solve for Kc?
Yeah.
Yes. And that's all I'm going to do here. And there's my Kc under those conditions. Everybody comfortable with that? Once again, it seems a lot easier when I do it. Make sure that you're comfortable with the context, the information, and how to use it on your own. Okay. So there is the first introduction to ice. The ice table can be used to determine equilibrium concentrations of reactants and products from the initial concentrations given. Of course, they won't all just be A going to B. And you'll have to factor in all the other things we learned as we build out that concept. Okay, so let's take a look here. Always got to know, first thing, I'm going to train you this way right away, what is your equation?
Right.
Everything is coming from, if you don't understand your equation, and this will play a bigger role later, then you're going to make all kinds of mistakes. You're going to get lost because you don't know what your foundation is. I'm saying anchor yourself to the equation. And everything you do from ice and from here on out, make sure you know the equation and then solve accordingly.
Right.
If you don't anchor yourself to the equation, then you're just floating. Because the equations, as we know, are not always just one. And sometimes you have to use multiple equations in order to get what you want. So if you don't know which equation you're using or how you're using it, then what's the ice table representing? Right. Okay, so we're at the very early beginning stages, and at the very early beginning stages, I want you to always know you must have this. Or you must be able to make this. Okay, and if you have that, now everything else should flow easier. Okay. 2 mole of each H2 and I2 are mixed in a 10-liter flask and allowed to come to equilibrium, 3.5 mole of HI is produced. What is the value of the equilibrium constant for this reaction? What is the very first thing I should do is make sure I know this. Now what's the next thing I do? Make a nice chart, thank you. I, C, E this way. Now what's the next thing I do?
So you got the start.
What's my I for H2? I'm just going to put it right under here. What's my I for H2? It's going to be 2 divided by 10, right? So that's 0.2. And what's my initial for the I2?
Same.
0.2.
Yeah.
What's my initial for the HI?
0.
0.
Right.
I just figured out the first part of the ice chart, right? You don't know the change yet, so we'll forget C. E, what do I know about E?
Oh,
Do I know
Yeah,
anything
equilibrium.
about E?
Yeah.
In any of these 3 things, what do I know?
you know when it.
HI. For the
So I know 0.35 molarity is my equilibrium
Right.
for HI,
Yeah.
right? 3.5 divided by 10, right? Because the volume did change. Do I know these? Not yet. Can I figure out the change now that I know it went from 0 to this?
Yes.
What did it change?
It was-
Positive
Uh-huh.
0.3.
0.35, right? Molar. 3.5 divided by 10. Okay. So that's a positive. This is a 2 to 1 here, right? So this is 2. That means half of that should be my change here, and half of it should be my change there.
Yeah.
And that should be negative because I lost that amount. These are reactants that went to products. Now I could say whatever I started with minus that gives me my equilibrium amounts of the H and the I. And then, of course, from there I could just put together my Kc. Everybody see how that worked? Okay, let's go ahead and do it. So that's what's known. We figured that out already. Remember, the 0.2s are just because I only gave you a mole. You had to figure out the molarity, which is dividing by the volume, which was 10, if I recall. So at 0.2, 0.20, 0.3, the difference here is going to be a positive 0.35.
Yep.
And since that's 2, and these are 1, it's a 2 to 1 ratio, that's half. So half of 0.35, 0.17 or something like that. And 0.17, but these are negative because I lost those.
Yes.
Okay. Then this minus this gives me this. This minus this gives me this. And these are my equilibrium concentrations of this reaction at that temperature. And of course now I can figure out Kc. What's that?
2 to 1 ratio, what is that? Because you have 2 HI?
Coefficients. My coefficient here is 2. That means I have 2 moles of this versus 1 mole of this and 1 mole of that. So that 2 moles of this is what changed, means I lost only half of a mole, or half of this. That cuts in half, that cuts in half. Based on molar ratio.
Yeah, you can divide it by 2.
Molar ratio, this is the molar ratio, 1, 1, 2.
Yeah.
So the change is going to be according to that ratio.
It would be the 0.35 divided by 2, you get the other.
And since I figured out the product,
Right.
then I have to extrapolate back to the reactants.
Right, instead of multiply.
If I was given something I could figure out the reactants, then I'd have to extrapolate up to the product. It all depends on what information you have. In this one, you have the initial and the equilibrium of the product only, so then you use the change accordingly.
Right.
So you did 0.35 divided by 2.
Right.
To get 0.175.
Yep. That's just because it's a 2 coefficient in the product and a 1 coefficient in both reactants.
Nice.
If one of the reactants had a 3, then I'd have to adjust accordingly.
Right.
So that's ice. Right? Okay, cool.
But you said it if
And now I can solve for Kc with that information because I know I'm at equilibrium concentrations.
so if let's say like the molarity of one of them actually would have been 2, then you multiply the 2 of the 175?
The coefficients.
Coefficients, right?
You have to just adjust depending on whatever those coefficients are. I just gave an example. If you had a 3 on 1, then you'd adjust accordingly.
Multiply, right?
I'd probably just go 2 to the 1 and then 1 times 3. But you could go 2 divided by 3 or whatever you wanted.
Awesome.
Or 4 or 5 or 6 or 2, whatever it is. That's what it is.
And the initial values for H2 and I2, was it 0.2 because of the subscripts?
Given.
That was given.
2 mole
The 2.0
in a 10 liter.
mole of volume?
Yep.
Oh.
You gotta
On the
put it in
notes here
molarity?
it says 1 liter.
You wanna put it in molarity?
Yeah, and ours is
Oh,
just
yeah,
one.
that's
Yeah.
why.
It's giving mole over volume,
Okay.
which
And,
is your molarity.
It's written wrong.
Yeah,
Okay.
ours
Yeah.
is.
So just adjust it.
Okay.
Not a big deal.
And if it was 2, let's say, then I could do this whole thing with 2.
Right.
Just to make sure, so when I find KFC, that value just kind of, it's basically telling me if the products or the reactants are favored, right? Because we got a numerical value, so that
So
value-
are you going to this slide here?
Right.
Yeah.
And you have a KC of 196, so then that tells you, what is it you want to know?
Equilibrium.
That number basically just tells you if the reactants or the products are favored, right? The KC?
That tells you at that temperature. One of the things it can tell you is if you're interested in that, it can tell you that, yes. Right? You may not be interested in that, but if you are, then this is 196. Is this going to fit? Am I going to have a higher concentration of products or a higher concentration of reactants?
Products.
Products.
Right.
So it does say, it can tell you that if you're interested in that, yeah.
What else can I tell
Absolutely.
you?